Hi, Jace. Here's my video for the first question there. Ignore the confusing work here. I'll explain through it first. Um, we've got our equation that we want to prove right here. And well, there's two different possibilities because we don't know the relationship between A and B. Two possibilities are that the intersection between A and B is an empty set, and we're in right here. So there's no crossover, there's no mixing in between A and B. That's situation one. Situation two is there is no the intersection between A and B does not uh, equal a empty set, meaning that A and B do cross over each other and they do intersect. So we have to prove for both situations what would happen, and we have to prove for both of these situations, both of these two situations, that this statement is always true. So let's first start where there is no intersection between A and B. The intersection between A and B is an empty set otherwise. So, um, well, let's think about what this part of the equation means first. A minus B is basically saying let's take a cookie cutter of B and cut out any intersecting parts of A. And whatever's left of A is our new subset, or is our new set. So in this case, if we did take a cookie cutter of B out here, it wouldn't touch anything of A because there's nothing in common due to this statement. So if I imagine I did take a cookie cutter, try to cut out A, I wouldn't cut out anything. What I'd be left with would just be A. So in this situation where there's no intersection between A and B, A minus B is equal to A because there's nothing for the cookie cutter of B to cut out. So now we get this brand new equation because we can just substitute in A minus A into our original equation up here. So this blue part has the domain of A, wherein wherein X is an element of A, obviously. And now talking about this union part, that is basically everything in red here, so everything in A and everything in B. That has the domain of X, wherein X is an element of A or X is an element of B. And obviously, we can see, you can write out the formal proof for this. I'm just going to kind of glimpse over it in verbal. But if X has to be an element of A, and in A union B, X has to be an element of A or an element of B, we can clearly see that they both share this part of underlined orange, that X can be an element in A. Perfect. Now, that's situation one. And actually, wait a second. Before I go on to the next one, I drew some diagrams here just to better demonstrate my, because it said in the question to you could promote your or support your answer with Venn diagrams. So here's a couple of Venn diagrams for you. So we've got A minus B in blue here. So this is, remember the cookie cutter, but since they don't overlap, there's nothing that cuts out of A. So A minus B is literally just A. A union B is everything in A and everything in B. And we can see that when we overlap the two Venn diagrams, the blue and the red, the blue is a subset of the red. So A minus B is a subset of A minus, or A union B, excuse me. Great, so that's the situation if there is no intersecting parts. But what if there is intersecting parts? What if they do intersect? Well, simply put, we can just start going through the domains again. So in this case, A minus B would have a domain of, well, that would be, I'm going to write it in green here. So that would be, in this Venn diagram, it would be everything in the green here. So if we took the cookie cutter of B and cut out everything in A, or cut out whatever it was overlapping it with in A. So it'd be this section here, and this green section has the domain of, I'm going to change color just to prove my point. It has the domain of X is an element of A, wherein X is not an element of B. Great, okay, so we got that in mind. Now over here in, well, I guess this is also red. So this is A union B, so that's basically everything in A and everything in B. Now, again, you can write out the formal proof for this, but if we know that A is A minus B contains elements of A, and A union B contains elements of A or B, well, therefore, since there's elements in here there, X can be an element in here and an element in here, A minus B is a subset of A union B. And now we've proved that even if there isn't an intersection or if there is an intersection, that this statement is always true. And lastly, before I sign off, I also drew a couple Venn diagrams up here for if they are intersecting, and they're just up here. So again, our A minus blue and B is this section, our A union B is this red section, and when they overlap, they we can see that the blue is a subset of the red. I hope that helps. I'm sorry it was kind of pretty layman's terms, but yeah, hope that helps.